Hello, hello, hello. This is Coach Ikram and welcome to this video on individual gas laws. In this video, we're going to discuss Boyle's Law, Charles's Law, and Gay-Lussac's Law. So we're going to kick things off with Boyle's Law. Boyle's Law discusses the relationship between pressure and volume when your temperature is held constant. And it's notated by this equation right here. P1 V1 equals P2 V2. And Boyle's law states that as pressure increases, volume decreases. And as pressure decreases, volume increases. This is going to be an inverse relationship between pressure and volume, which should make sense when you look at it algebraically up here. Visually, if you look at it, you've got a piston over here on the left-hand side. It's got a pressure of 100 millimeters of mercury, and it's got a volume of 1 liter. If you notice on the right, we have increased our pressure by 2, times it by a factor of 2. So now we have a 200 millimeters of mercury of pressure. Therefore, our volume has been decreased by half in that inverse relation. If you look at it graphically, if you graph pressure versus volume, you're going to end up with this inverse curve right here. But if you graph it, because it's an inverse relationship, if you graph it volume versus 1 over P, the inverse of P, you're going to end up with this positive slope. And that just gives you a good graphic representation of Boyle's law. So like I said in the previous slide, we're going to use P1V1 equals P2V2 as our Boyle's law equation to solve for various variables. So in this example, it says a high altitude balloon contains 30.1 liters of helium gas at 103 kilopascals. What is the volume when the balloon rises to an altitude where the pressure is only 25.4 kilopascals? So I'm going to plug this into P1V1 equals P2V2, and I'm going to solve for my new volume. So my givens are 30.1 liters of helium gas. I've got a pressure here of 103 kilopascals and a new pressure of 25.4 kilopascals. So my equation is P1V1 equals P2V2. My original pressure was 103 kilopascals. My original volume was 30.1 liters. My original, my new pressure, is 25.4 kilopascals. And I don't know my new volume, so I'm going to leave that as the variable V2. Now I'm going to rearrange my equation and divide both sides by 25.4 kilopascals. Note that my kilopascals cancel on the left, and I'm left with liters, which is what I'm looking for. I'm going to solve the algebra, and I'm going to get V2 equals, with 3 significant figures, 122 liters. And that is my new volume. And this should make some sense. If you look at your original equation, your pressure is cut by about a factor of 1/4. It goes from 103 down to 25.4, 1/4, which means that your volume should quadruple. And if you look, it goes from 30.1 to 122. So that makes sense. It's a reasonable answer to what the problem is asking you if you understand the concept of Boyle's law and that these are inverse. The next law is Charles's law. Charles's law is the relationship between volume and temperature when your pressure is held constant. So in this case, we're going to be using the equation V1 over T1 equals V2 over T2. So Charles's law states that as temperature increases, volume also increases. And then as temperature decreases, volume decreases, which means that this is now a direct relationship. So if you notice here, we've got a piston over a heat source, and as we heat it up and we're increasing that temperature, our volume increases because the gas moves faster, kinetic energy increases, the gas particles move faster, and therefore, if it's a flexible container, the volume is going to increase. And remember, pressure is held constant, so in this case, we are dealing with flexible containers. The relationship between volume and temperature when the pressure is held constant is direct. And so if you look on this graph, you'll see we've got volume in a different language, but you can still read it. Volume versus temperature, and you'll see that it is a positive. So working a problem with Charles's law, a balloon inflated in a room at 24 degrees Celsius has a volume of 4.0 liters. The balloon is then heated to a temperature of 58 degrees Celsius. What is the new volume if the pressure is held constant? So I'm going to go ahead and solve this problem using my V1 over T1 equals V2 over T2. So when I plug in my values, my original volume, V1, is going to be 4 liters, 4.0 liters. My original temperature is 24 degrees Celsius. However, we cannot use Celsius in any of these problems. We have to convert it to Kelvin. So I'm going to take 273 plus the 24, and I get 297 Kelvin. My new volume is what I don't know, so I'm going to keep that as the variable V2. And then T2 is going to be 58 degrees Celsius. Again, I'm going to convert that. So 273 plus the 58, and I get 331. So that's my new temperature. I'm going to solve for V2 by rearranging the equation, basic algebra. And I'm going to get V2 is equal to 4.46 liters. The final law that we're going to talk about is Gay-Lussac's law. And his law discusses the relationship between pressure and temperature when your volume is held constant. So his equation is P1 over T1 equals P2 over T2. So here you're talking about pressure and temperature. Your volume is constant, so we're not worried about it. Pressure and temperature, as temperature increases, pressure also increases. And as temperature decreases, pressure decreases. And remember, all of this is in a fixed container where your volume is not going to change. And this is also a direct relationship. So you should see some algebraic similarities between this law and Charles's law. They're both direct relationships, and so the algebra looks very similar, as it should. And looking at it graphically, you should also notice some similarities between this law and Charles's law. We've got pressure versus temperature here, and it is a direct relationship. As your temperature increases, so does your pressure. So solving a problem with Gay-Lussac's law, the gas left in a used aerosol can is at a pressure of 103 kilopascals at 25 degrees Celsius. If this can is thrown into a fire, what is the pressure of the gas when its temperature reaches 928 degrees Celsius, which is extremely hot? So I'm going to go ahead and solve using my equations. We have P1, T1. Oops, sorry, that was completely wrong. Sorry about that. P1 over T1. I almost started writing Boyles Law there. And then P2 over T2. I'm going to go ahead and fill in my variables here. I've got an original pressure of 103 kilopascals. I've got a new or original temperature of 25 degrees Celsius. I'm going to go ahead and add 273 to that. So I get 298 Kelvin. I don't know my new pressure, so I'm going to leave that variable as P2. And then my new temperature is 928 plus the 273. So I'm going to get 1201 Kelvin. I'm going to rearrange the same way I did last time, times both sides by 1201 Kelvin. Note that it crosses off your Kelvin and all you're left with is kilopascals, which is an appropriate unit for pressure. And when I solve, I get three significant figures, 415 kilopascals. The important thing to remember with some of these problems is your units. Make sure that your units cross off and that you're left with the appropriate unit for what you're looking for. And the second most important thing is significant digits. Remember, when you're adding temperatures, you are following the addition and subtraction, particularly going between Celsius and Kelvin. You have to follow the addition and subtraction significant figures rules, and those are separate from your multiplication and division significant figures rules. So just keep that in mind when you're doing your conversions before you plug into your equation. That is the end of this video. Go ahead, rewatch it if you need to. Make sure you take good notes and come to class with questions. Thanks.